my friends, welcome back. Still part one. Sorry, it's kind of long. It takes some time to kind of get going. Again, you will find your homework assignments to be refreshingly short, so all the energy, most of the energy is going to go into your notes for this stuff. Just basic differentiation rules again. So moving forward, let's talk about the constant multiple rule. So I'm going to go ahead and just write this in Leibniz notation. Hopefully you're starting to get comfortable with it. The constant multiple rule is for where you're taking the derivative with respect to x of a constant times a function of x. So this will be something that you'll memorize. I think I'm going to go ahead and let you think about what that rule would be. And then this is actually something that you can discover within a proof. So I'm going to go ahead and just kind of get started here. So if you're taking d dx of a constant times a function of x, then if you were to apply the definition of derivative, you would get the limit as h approaches 0 of, and if this is the function rule you're taking the derivative of, then this function rule with x plus h subbed in would be c times f of x plus h minus the original function as is, c times f of x all over h. And then if you look at what I've got on top, you can factor the c value out. Times and then using a property of limits, you can factor constants in front of a limit statement. So constant factors, that is. So c is a constant, so we could factor it out front. So we'd have c times the limit as h goes to 0 of f of x plus h minus f of x all over h. And this is one of the times where we get to find out if you have been sufficiently tortured by the definition of derivative. And if you have, then you could look at this statement right here after the c and you could say, oh, I know what that is. And you can kind of put Humpty Dumpty back together again. So this entire expression...
Look, I found under the couch.
Oh my goodness, I was looking for that.
And also a penny.
Oh my goodness. My poor son has become so bored that he's looking under the couch for lost treasures. Anyway, he's finding things, so that's nice. All right, so if you've been sufficiently tortured by definition of derivative, you could look at this mess and you could say, that is f prime of x. So what did we just find out? Basically, you can, if you're taking the derivative of a constant times a function of x, you can basically factor the constant out front and take the derivative of the part that's left. And that would, of course, be f prime of x. So I'm going to bring the prompt down. And so that's the rule. You can factor the constant out front. And then d dx of f of x is just f prime of x. There we go. That's the rule. Let's put a little end to our proof here. Okay. Now let's do an example that practices using it. Let's see. Are we on example 5, I think? Okay, the directions are for you to differentiate the function. Let's give you part A. Let's say I give you... let's see, y equals just 5x cubed. Okay. I am going to show two versions of this. The first version is showing lots of steps to make the thinking clear, and then the second version is where you either show one or no steps, and everything's okay as long as you can consistently do it correctly. So notice that the prompt is y, not f of x, so which means we'll do our work and our answer all in Leibniz notation. So I'm just going to show, we're going to take d dx of the left side, and we're going to take d dx of the right side. Remember, you always write d dx on the left side of what you're taking it of because it's a function. So on the left side, notation for d dx of y is dy dx. On the right side, we could use the constant multiple rule for derivatives, and we could pull the 5 out in front. And then we just have to take d dx of x cubed. Now this is a power rule problem right here. So we'd have dy dx, and then the 5 just gets multiplied by whatever we get for the derivative with respect to x of x cubed, which would be 3x squared. Your final answer, with more steps than we will probably ever show again, would end up being 15x squared. So if you look at what just happened there, I hope it makes sense that really, in a way, it's as if you just have 5 and then times the derivative of this. So the 3 kind of gets multiplied by the 5, gives you the 15. You take 1 from the power, you get the 2. So if you want to skip this step, and this step, and jump straight from the original problem to the answer, you have my blessing as long as you don't mess it up. All right, but the steps are there if you ever need them to keep things straight, okay? All right, let's do something similar. Part B, let's say I give you, let's see, y equals, and let's give you something very similar to what I just gave you. Let's give you 5x, and this times quantity cubed. So this is a good time to pause the video and do what you're going to do with it. I will tell you this one is kind of a sneaky one. So the issue with this one is a lot of people see a power rule problem right off the bat. And so they want to say the answer is 3 times the quantity 5x to the second power. They want to use power rule on it. But why can you not use a power rule on this? It's because your base is not just x. So it's very important that you look at the rule as far as what you can, when you use it, and then also how you use it. Okay, so this is not a power rule problem yet. But if you practice the art of algebra before calculus, notice I'm not saying dy dx, I'm just saying y still, then you could just cube it out using properties of exponents. So you get 5 cubed, which is 125 times x cubed. Then if we took d dx on both sides, and I will show some unnecessary steps just to make sure that I am being clear. Then on the left side, d dx of y is dy dx. On the right side, you could factor that constant out in front and just take d dx of the function of x that's left. Now this is a power rule problem. Your base is just x, and then you're taking and then your exponent is a constant. So dy dx would be 125 times 3x squared for the derivative of x cubed. Notice I write d dx until I do the derivative, then it's important that you stop writing it, okay? Your final answer would be dy dx is equal to, I think, 375x squared. Okay? All right, for all of that work, I would say that cubing it and writing it as 125x cubed is necessary. The step where you just showed d dx on both sides is not necessary. Factoring the 125 out should happen in your head, but you wouldn't especially have to write it down. And then this step is also something that could happen in your head. So if you can jump straight from right after you cubed everything, turned it into a constant rule / power rule problem, and then jump to here, you can do so with my blessing. But this is the stuff that goes inside your head, however. Okay. All right, my friends, let's see. Let's take this to another level. Let's talk about the sum and difference rules. for derivatives, that is. Okay, so this would be for where you're taking the derivative with respect to x of one function of x. Let's talk about the sum rule first. So plus another function of x. So in this situation, go ahead and I would say guess as to what you think you can do. Okay. And then we'll go through the proof. Okay. So the proof would be, let's prompt it by what we're finding. So we're finding d dx of f of x plus g of x. And so we're going to fall back on the definition of derivative for the purpose of the proof, and then we'll get a fun little rule. And then anytime we're in a situation like this, we get to not do the hard way. You get to use the rule. So if f of x plus g of x is your function that you're taking the derivative of, then according to the definition of derivative, we'd get the limit as h goes to 0 of this exact thing with instead of x's, x plus h's. So it would say f of the quantity x plus h plus g of the quantity x plus h. And then we would subtract this function as is. And all over h. Okay? Now, from here, we would distribute the negative in, and then I'm also going to regroup things. So the f stuff is all together, and then the g stuff is all together. So I'm going to rewrite it as the limit as h goes to 0 of f of the quantity x plus h minus f of x plus g of the quantity x plus h minus g of x. Notice it's minus because you'd have to distribute the negative in. And then it's all over h. Then I could rewrite this as the limit as h goes to 0 of so let's think about what fractions could we add together to get this result. Well, let's keep the denominators both h, so you have common denominator. It would be this denominator. And then let's put f of the quantity x plus h minus f of x on this one. That would give you this part back. And then the rest, g of the quantity x plus h minus g of x all over h. The next step is where you use a property of limits and you distribute the limit over addition. So we could rewrite this as the limit as h goes to 0 of f of x plus h minus f of x all over h plus the limit as h goes to 0 of g of x plus h minus g of x all over h. All right, another place where we get to find out if you've been sufficiently tortured. If you look at this first limit statement, hopefully if you put Humpty Dumpty back together again, you could say, oh, I know that. That's the definition of f prime of x. And then limit as h goes to 0 of g of x plus h minus g of x all over h. That, my friends, would be the definition of g prime of x. So what were we doing in the first place? We were taking the derivative with respect to x of one function of x plus another one. And what did we find out? Basically found out the derivative distributes over addition. So that's what you can do. And what's short for d dx of f of x? It's f prime of x. And short for d dx of g of x, that's g prime of x. There we go. Okay. Now that's the sum rule for derivatives. Just basically says that derivatives distribute over addition of two functions of x. If you have subtraction here, I hope it's not a big surprise you'd have subtraction here. The proof is so similar to what we just did that I don't think we'll bother with that. Okay? All right. So do know this plus or minus notation is just us writing two rules in one statement. Okay. Example, are we on example 6? Yes, we are on example 6. Okay. This is going to be an exercise in making sure that you can kind of think about what you're doing. So we're going to show more steps than usual. So the directions are for you to differentiate the function using only one property at a time. And you're supposed to justify each step. All right, I'm only going to make you do this once. After this, you get to do this all in your head if you'd like. Just for the record, when I was in Calc 1, my teacher made us do an entire problem set of these. So I'm just gonna make you do it once because man, I hated doing a whole problem set. All right, so let's say I give you something like y equals 7x cubed minus 5x to the 7th plus 8. And the directions say we can only use one property at a time, and every time we have to justify each step. That means you have to say what rule you used or what you did, okay? So I'm gonna go ahead and show a first step of just taking d dx of both sides. Okay, reminder, my friends, I'm gonna be looking for this when I grade your work. If you write d dx, you always write it on the left side, and you write it on each side of the equal sign as well. So d dx of the part that's on the left side of the equation, d dx of the part that's on the right side. D dx is always on the left of what you're taking the derivative of. Okay, so if I was to explain that step, I guess I would just say take the derivative of both sides. Okay. Now for notation for the left side, d dx of y, also known as dy dx. Okay, now it says one rule at a time. So all the rules that we've talked about in this lesson, which one would make sense first? I hope it makes sense. The sum and difference rules would make sense first. So we're going to show that this is the same as d dx of 7x cubed minus d dx of 5x to the 7th plus d dx of 8. Some folks would want to argue 8 is not a function of x, but you could think of 8 as 8 times x to the 0, so I guess it kind of is. Anyway, so we just used the sum and difference rules. Okay, and we just broke the rules, I guess, of the problem, but it would be too painful, honestly, to show that in 2 steps. So we just used the sum and difference rules for derivatives. Okay, what rule next? What would make sense? And I hope it makes sense that right now this doesn't look like a power rule problem, but if it just said x cubed, it would. So let's factor the 7 out. Same thing with the 5. And then if you factor the 8 out, you'd have to leave a 1 behind, but I don't think it's worth our time, so let's just rewrite that as d dx of 8. So what property was that when I went from d dx of 7x cubed to 7 times d dx of x cubed? That was the constant multiple rule. Okay, now what rule would you like to use next? We could use power rule or the derivative of a constant, either way. So let's use power rule. I like power rule. So we'd have 7 times, and what's d dx of x cubed? It's 3x squared. Remember, exponent becomes coefficient, and you drop 1 away from your exponent for your new exponent. Minus 5 times derivative of x to the 7th is 7x to the 6th. Also, you write d dx until you do the derivative, then you stop writing it. D dx, actually, I'll leave d dx of 8 off because that's really not a power rule situation. Okay? So now, what rule did we just use? We just used the power rule. All right. I feel like with the power rule, we should never be able to just say it normal. We should have to say like, power rule. I don't know. Something like that. If this was in person, that would have been way funnier. Okay. Anyway, I'm going to simplify and also use a rule for this. So the spacing is just a little off. So we'd end up with 21x squared minus 35x to the 6th, and d dx of 8 is 0. I think I'll just go ahead and show it, even though that's a little weird. But I just want to show that I thought that through. And the rule that I just used is that the derivative of a constant is 0. There we go. All right, my friends. The last thing that we're going to do, by the way, okay, a comment before we do another example. I do not expect you to show all those steps when you do the problem set that I'm going to give you. Honestly, if you were to jump straight from this to the answer, which I should bring my prompt down. There we go. To the answer, if you can do it correctly, I'm just going to box everything but the plus 0, because the plus 0 is a little weird. If you can jump straight from y equaling 7x cubed minus 5x to 7 plus 8, straight to this, that's fine with me, okay, when it comes to your test, all right? Notice we are using, the point of this lesson is in certain prescribed conditions, we don't have to do the definition of derivative, we can use simple rules instead. Okay, speaking of that, let's look at example 6. All right. Directions are for you to differentiate. Let's say for part A, I just give you, and we're gonna give you as much practice with Leibniz notation as we can here. So y equals, let's give you 40x squared minus 19 minus, let's just do 19 over x. Okay, all right, try to stay ahead of me. Pause the video if you need to. So for a problem like this, I would recommend writing 19 over x as 19 times x to the negative 1, first of all. And then at that point, you can use a combination of the difference rule for derivatives, the constant multiple rule for derivatives, and power rules. So your answer would be dy dx equals 80x, I'll just say to the first. Negative 1 gets multiplied by the negative 19, makes it be positive 19. You'd have x, take 1 away from negative 1, you get negative 2. Your final answer, where you write it with no negative exponents and simplified, could look like this. 80x maybe plus 19 over x squared. Okay, be prepared, my friends, to practice the art of algebra before calculus, where you rewrite something so you don't do the derivative yet. You rewrite things to make it so that it is derivative rule friendly, and then you do the derivative after that. Okay, speaking of that, let's look at part B. Let's give you y equals the quantity x over x squared plus 1 to the negative 1. Now let's think about this one. Do we have a rule for derivatives of like a function of x divided by another function of x? That would be like a quotient rule for derivatives. Have we had that conversation? The answer is no. Do we have a rule for one function of x composed inside another one, like an f of g of x situation? The answer is no. So in a situation like this, we really don't have rules for the problem as is. So that art of algebra before calculus is all the more important. So let's think about what a negative 1 exponent would do to a fraction. I'll show this in 2 steps. By definition, it would be 1 over this base, kind of to the positive 1 power, which really has the effect of kind of flipping your fraction upside down. So if you flip and multiply, you just get x squared plus 1 over x. So now I got rid of the composition of two functions that we had that we don't have a rule for. But do we have a rule for one function of x divided by another one and taking the derivative of that? The answer is no, or not yet. So what you're going to need to do is a little more algebra. So I'm going to go ahead and divide that x in. So I'm still not calling it dy dx, I'm calling it y. And so you'd have x squared over x, which is x, plus 1 over x, which is equal to x plus x to the negative 1. Now we have the green light. This is something that we can use rules for. We have rules for the sum of two functions of x, and we have a power rule. So we would get dy dx, because I took d dx of that side, and then equals derivative of x is 1, and then derivative of x to the negative 1 is negative 1x to the negative 2. So likely the answer could be written, this is before we simplify it, but then it also could be written as 1 minus 1 over x squared. There's another version of it. And then watch out if this is multiple choice. One more version of the same answer would be where you got common denominator. And so that would be, so 1 is like x squared over itself. So you'd have x squared minus 1 over x squared. There we go. Your answer is most likely to look like one of the last two. Like so. All right, my friends, part C, and then we are done. And then you can do your fairly easy worksheet that goes with it. Okay, part C, let's give you y equals the quantity x to the negative 1 plus 2 times the quantity x squared over 3 plus 1. Okay, so if you take the derivative right now of both sides, then you'd need a rule for the derivative of one function of x multiplied by another one, and we have not talked about a product rule, so it's best if you try not to make one up. There are two things that could happen if you start making up rules for math. One is you could get a PhD, and the other one is that you could just screw up your math problem. Unfortunately, it's way easier to screw up your math problem than it is to earn a PhD. So let's make it so we don't have one function of x times another one. Let's get out of this situation that we don't have a rule for. So let's just distribute and multiply this sucker out. So if we did, when I do this, I tend to think of x to the negative 1 as 1 over x for this part. So 1 over x times x squared over 3, one of the x's would cancel. We'd have x over 3. 1 over x times 1 is just 1 over x, plus, now let's distribute the 2. We'd have basically 2/3 x squared, and then plus 2. Okay, a little more algebra before calculus. X over 3 could be thought of as 1/3 x, plus 1 over x is x to the negative 1. Like so. And now this is stuff we have rules for. We have sum rule, we have constant multiple rule, and we have power rule. So if you take d dx of both sides, on the left you'd get dy dx. On the right, d dx of 1/3 x is 1/3. d dx of x to the negative 1 is negative 1x to the negative 2. d dx of 2/3 x squared would be 4/3 x to the 1. And d dx of 2 is 0. Trying to simplify your answer, I could write it maybe as 1/3 minus 1 over x squared plus 4/3 x, or 4x over 3, same thing. This is one version of the answer that would be acceptable. Another acceptable version was where someone got common denominator, which would be 3x squared. If they did, their answer would be x squared minus 3 plus 4x cubed over 3x squared. So they would end up with, let's write that in descending power, so like 4x cubed plus x squared minus 3 over 3x squared. There we go. This is likely what your answer would look like if this was a multiple choice problem. Okay? All right, my friends. So please notice there's a lot of algebra involved in being able to, number one, put yourself in a position where you can use the calculus rules. And then number two, put your answer in a form where you'll be able to choose it in a multiple choice situation. And whether you're taking the Calc AB or the BC test next year, half of your test experience at the end of the year for the AP exam will be multiple choice format. So you'll want to be able to choose your answers out of a lineup. And that just requires quite a bit of algebra. All right, my friends, I hope this helps. I hope you enjoy the worksheet that comes with it. Take care, everybody.